So using Hankel contour representation, to evaluate zeta s for s belonging to the integers, of course s not equal to 3, obviously. That's an unsolved problem determining the values of the zeta function and not positive integers. Okay, so what we do is this. Start by writing 1 over e to the z minus 1. Start by considering, say, 1 over e to the z minus 1 plus half. So something very interesting happens when you add half to this. So you get in the denominator 2 times e to the z minus 1. And the numerator, you get e to the z plus 1. So we can now rewrite this as, I'll multiply numerator and denominator by e to the z, e to the minus z over 2. So I can write this as e to the power z over 2 plus e to the minus z over 2 divided by 2 times e to the power z over 2 minus e to the minus z over 2, multiplying numerator and denominator by e to the minus z over 2. And when we do this, this is equal to the hyperbolic cotangent of z over 2, 1/2. And therefore, this is an odd function. All right, so what does that mean? Therefore, if I multiply by z, this is an even function. Now, this multiplication by z, you can multiply by z cubed, you can multiply by z inverse, any odd power of z, and you will get an even function. But what is the role of this z? The role of this z is that this e to the power of z minus 1 has a pole at z equal to 0. Asymptotically, e to the z, when z is close to 0, is 1 plus z, asymptotically. Therefore, when I subtract 1, this behaves like 1 over z. Therefore, multiplication by the z at the top removes that pole. And therefore, this object is now an analytic function at z equal to 0. We don't have to worry about that part. So the observation that we make is multiplication by z as 2 creates an analytic function at z equal to 0. Thus, we may expand the expression in 2 as a power series in z about the origin, because it's an analytic function. Okay? Thus, right? Z above 0. And what does this actually lead to? Yielding. See, this is an even function. So when I do it as a power series in z, I'm only going to get even powers of z. But then I have to add the z over 2 by itself. So that's the only lone thing other than the even powers of z. Okay, so that has got an important feature that we will understand later, that there is a role for the z over 2. So what does this yield? So this yields z over e to the z minus 1 is equal to, now we write this as a power series of here, put the 1, I bring the z over 2 to the right-hand side, and then I've got a power series, and the coefficients of the power series are typically written in this form. We write factorial because they're exponential function. Okay. All right, so this is really summation minus 1 to the n bn z to the power 2m over 2m factorial, m from 0 to infinity, and then there is, of course, a minus z over 2 on the side. Now, I'm not getting into the details here. I will need a separate study of Bernoulli numbers where the bn are the so-called Bernoulli numbers. And they are positive. So, so that takes a little bit of work to show that they are positive. But the important thing is this. Sometimes people, so here I have the Bernoulli numbers as I've written are only defined as coefficients of the even powers of z. Sometimes you can define the Bernoulli numbers, some people define the Bernoulli numbers for all integers, and simply declare the Bernoulli numbers at the odd positions as 0, and so this bm is replaced by b2m, with the only exception that b1 is, so I'm not calling this b1, I've separated this out, so this is like a minus half. Okay, but this is it, and Rademacher's book that I have given as a reference to you has a full section on Bernoulli numbers and its properties, but I will come back to this later in the lecture. Okay, so this is the expansion that we have. All right, so having done this, I now state a theorem. Okay, so this leads to theorem. So the theorem is the value of zeta s at integers s is given by the following. 1, zeta 0, it is minus half. This we already know. Right? Zeta 0 is minus half is something we know. Zeta minus 2m is 0. We will actually deduce this from the Hankel contour. But more interestingly, zeta 1 minus 2m, so here m is positive, by the way, positive integer. Zeta 1 minus 2m is now given in terms of Bernoulli numbers. So it's minus 1 to the m bm divided by 2m. Okay, this is one theorem, one part of the theorem. The second part of the theorem is that for m greater than or equal to 1, zeta 2m is 2 to the 2m minus 1 pi to the 2m bm over 2m factorial. So this is Euler's formula. So Euler was the one who first proved, who evaluated the Riemann zeta function at even integers. In fact, to just mention a mild history here, the formula was proposed by the Bernoullis, who were, it's a family of mathematicians, father, son, and so on. And they were very competitive. So they used to pose problems and challenges and all these things. And Euler was a student of the father Bernoulli. So one of the problems that the Bernoullis posed was, it was called the Basel problem. It was very famous at that time. Was evaluate zeta 2. They didn't call it zeta, but I'm just writing it as zeta 2. Summation 1 over n squared. So no one knew how to find the value of this. And this was one of Euler's first discoveries which propelled him into world fame. So Euler was the one who showed that zeta 2 is pi squared over 6, and then later he was able to find the value of zeta 4, pi to the 4 over 90, and zeta 6 in terms of pi to the 6, and so on. So all of this was given in terms of even powers of pi. Okay, so he became world famous because of this. Okay, so this is a formula to divide. The Bm are rational numbers, so maybe I should just say that, right? I just said greater than 0, but actually the Bm are rational numbers, so we put Q plus. All right, so let us prove this. So unless I tell you what Bm is, I've not really solved the problem completely, right? But they are some rational numbers. Okay, so, but they're coming out of this expansion. So let's prove this. All right, so for the proof, what we do is this. Let S be less than 0, be an integer. Then that integral Is that we gave before is nothing but the integral over that circle of z to the s minus 1 dz over e to the z minus 1. I should put circle as z equal to a rho. Remember, the rho was between 0 and 2 pi from the last lecture. Now, you will say, no, this is a Hankel contour, so it's coming from infinity all the way down, and then there is a loop, and then it is going back. But keep in mind that the infinity thing with the two cuts makes a contribution only if s is not an integer, because only then that the multivaluedness of the logarithm makes a contribution. Because if s is an integer, it doesn't matter whether you write log z plus 2 pi I, because when I multiply that with an integer, e to the power k 2 pi I anyway is 1. So the contribution is cancelled because we're going in the opposite direction. So the IFS is given purely by this integral when s is an integer, right? But now, this is z to the s minus 1, which we will now write as z to the s minus 2, and then we'll put z over e to the z minus 1 dz to take advantage of this expansion. So this is then equal to the integral over absolute z equal to rho of z to the s minus 2 times minus z over 2 plus this series. Now, when we integrate powers of z over a circle, the only integral that contributes is 1 over z. Every other integral vanishes. So, in this expansion, 4. So in 4, the only term that will contribute will be the one corresponding to z to the minus 1.
This is really just the residue theorem, right?
That's all. Yeah. And there are no other codes for this thing. So this will, the only term that will contribute is z equal to minus 1. So all we have to do is to look at z equal to minus 1 and see what we get. Correct. So, okay, all right, so now let us look at 3 cases. Case 1. S equal to minus 2m, negative even integer. Well, if s is minus 2m, which is a negative even integer, including 0, although I'll treat 0 separately, okay. You have this as a negative number, less than 4, less than minus 4. These are all, should have corrected 2m. So these are all even exponents in this case, so they contribute to 0. The only odd exponent arises from here, but that odd exponent will either be minus 3, minus 5, or whatever, so this will all be 0. So yielding, in this case, I of minus 2m is 0. But now what is the formula that we got for IFS, if you recall? It's the IFS times gamma something, okay? So recall that zeta s is e to the minus I pi s gamma 1 minus s IFS divided by 2 pi I. We proved this on Wednesday, okay? And so from 6, we get zeta minus 2m 0. This is, of course, a fact that you already know, but I'm getting it from the Hankel conjugate. We did that previously from the functional equation. But it doesn't matter. This Hankel contour also led to the functional equation. But this is going to give you some other equation. Okay? So we have that. Now, what about I0? So now I put s equal to 0. When s is equal to 0, this is z to the minus 2. So attach it to the z, you will definitely get a contribution because you've got 1 over z. Right? But you have a minus half, so you will end up with minus half times 2 pi I, because I did put there is no 2 pi I here. This is just a Hankel contour. So it's I0 is minus half times 2 pi I. So plugging into 6, gives zeta 0 equal to minus 2. But this was something we did use by other means previously, but now we're getting it from the Hankel contour formula. But now let's see what we get with 1 minus 2m, and that's the new thing. All right. Put s equal to 1 minus 2m, negative odd integer. So if I put s equal to 1 minus 2m, this is minus 2m minus 1. So I have to pick up the coefficient of z to the 2m. So that's going to be, so this yields I of 1 minus 2m is equal to minus 1 to the m bm over 2m factorial multiplied by 2 pi I. All right, which together with 6 gives zeta of 1 minus 2m, the 2 pi I cancels, and I think that this is a minus 1 to the m, gives you a minus 1 to the m, but now you've got gamma of 1 minus s, which is now gamma of 2m. And then you've got your I, which is bm over 2m factorial, minus 1 to the m. The gamma of 2m is 2m minus 1 factorial, so you get minus 1 to the m bm over 2m. Therefore, establishes 1. So this Hankel contour is pretty amazing. I mean, I was talking to Professor Li Shen yesterday. He is sort of the local authority, local max, as far as special functions are concerned. Okay, so So, you know what he does? Every time he feels bored, or he has some free time, he picks up Whittaker and Watson, the Bible on special functions. He goes through it, and every time some insight comes to him, because it's really, guys, the ultimate book on special functions. So I was talking to him about the Hankel contour. So Hankel first used this in the study of the gamma function, and it was actually a revolutionary thing because it gave a completely new way to understand the gamma function. And now, I just want to say, yesterday at the thesis defense of Todd Molnar, when he was referring to this fundamental work of Selberg, which was one of the things he was using in his thesis, he was referring to Selberg using the Hankel contour to evaluate the generalized divisor function, and from that, the local distribution of the prime factors. So the Hankel contour is an extremely fundamental object, and it's very subtle because you've got this radius rho, and you've got the freedom. You can either shrink it to 0, which we did, or you can expand it, which we did. When we expanded it, we wrote it as a square instead of a circle, but it doesn't matter. You can deform these things. Okay, so you have a lot of freedom in the Hankel contour. All right, so now let us get to the 2m. So to get part 2, again choose S is equal to 1 minus 2m like we did here, except we don't use this, we use the functional equation. But use the functional equation. So what is the functional equation? There were 2 representations for IFS that we got on Wednesday, and I didn't write it down then, and I told you, equate the 2 expressions, and you will get a functional equation for zeta s, which will not look identical to the functional equation that we obtained, because there is a factor sine pi s over 2. But the 2 versions that we had, the original version and this version of Riemann, are the same, because they are connected by the relationship gamma s gamma 1 minus s is pi over sine pi s. So that's the connection between the 2, right? So we use the functional equation. And if you use the functional equation, this gives, to evaluate zeta 1 minus s. Zeta s is connected to zeta 1 minus s. And s is 1 minus 2m. So this is zeta of 2m, all right, in the form. So if you go back, you'll end up with zeta 2m is equal to minus 1 to the m bm over 2m that we wrote down, this value that you get. That is zeta s is connected to zeta 1 minus s, right? So this is the s. S is now 1 minus 2m. We have just evaluated that. Multiplied by the other factors. 2 to the 2m minus 1, pi to the 2m, minus 1 to the m over 2m minus 1 factorial. This 2m minus 1 factorial is gamma 2m. So I put it as gamma 2m, so that you recognize that this is coming from the functional equation. Okay, gamma 1 minus s. And that is precisely what I have here too. Okay, so 2m minus 1 factorial plus the 2m, which is 2. Okay, so this just shows another use of the Hankel contour. Now you might ask, sir, how come the odd zetas are not part of this story? Why is it that it's not possible to do the odd zetas? Well, for the positive odds. So that's a remark. If this approach is used to evaluate zeta of a non-positive integer, then what happens? Let's quickly check this 2m minus 1 or 2m. All right. So then I have to choose s equal to 2m plus 1, right? 2m plus 1. Right. S equal to 2m plus 1, which gives 1 minus s equal to minus 2m. But then the problem is that zeta minus 2m is 0. And you have got the sign factor, okay? And the sign factor gives you sign, yeah, 2m over 2 is 0 as well. So you just end up with 0 equal to 0, which is useless, of course. True, but useless. So this approach does not give you the value of the Riemann zeta function of the odd integer argument, but that doesn't mean some other approach may not give this. But people have failed to obtain a value of the Riemann zeta function of the odd integer arguments. In fact, there was this famous unsolved problem. So first thing, let us make a comment here, is that pi is transcendental. So what does transcendental mean? Transcendental means like E, pi can never be obtained as the root of a polynomial equation with integer coefficients. Now that fact was proved only at the end of the 19th century, whereas all the Hankel contour and so on were all in the middle of the 19th century due to Riemann and others. So the end of the 19th century was really a crowning period in mathematics. On the one side, the prime number theorem was proved. On the other, pi was proved to be transcendental, and therefore this famous problem of squaring the circle going back to the Greeks was solved. I do not know whether in American schools in geometry they talk about the three problems of antiquity, but in India, in our schools, when we do Euclidean geometry, they do mention the three problems of antiquity. I think they mentioned to me, but I'm much older to her. I don't know, they may have been spoiled by the American influence and much less might have been done. So, the three problems of antiquity are to square a circle, that means to construct a circle of a square equal in area to a given circle, which means construct square root of pi by ruler of compass, doubling the cube and trisecting the angle. So where you mentioned this in, I don't know,
we
did they mention
have
this in
that in class 10 exams.
something, yeah, at least it's mentioned in India. I don't know whether it's mentioned in America. No. So you see, these are great problems. So the problem of squaring the circle was settled in the negative when pi was proved to be transcendental by Lindemann, I think, right? So that was one of the greatest achievements of the 19th century. So since pi is transcendental, every power of pi is automatically transcendental. That means, in particular, not only are the even zetas transcendental, because of this, they are obviously irrational, and hence irrational. So the question was, is zeta 3 irrational? That was the question. That was a sensational, I mean, it was unsolved. Don't even worry about evaluating it. Can you even prove that it is an irrational number? So this French mathematician, Roger Apéry, stunned the world in 1978 by proving, yes, it's an irrational number. But the way he proved it sort of also was stunning and irritated the classical French school, the Bourbaki, the people who are used to all this rigorous mathematics. So I had just finished my PhD and joined University of Michigan in Ann Arbor, and then the news came that Apéry in the summer, that Apéry had proved the rationality of zeta 3. So there was a lot of excitement in Ann Arbor at that time and other places about this. And that's how briefly for that 1 year or 2 years I got into the subject of irrationality. But anyway, the way Apéry did this was he discovered these fabulous recurrences, sort of like a Ramanujan-like phenomenon, right? I mean, and so he was giving this lecture at a conference in Marseille, and then he said, I'm proving that zeta 3 is irrational. Now, Apéry was already considered to be a somewhat eccentric mathematician by the sort of elite French community, so he was sort of disregarded as sort of a semi-lunatic, okay? Crackpot of some sort. So people didn't take him serious. Every time he would lecture, there would be people in the back laughing and smiling, and they would throw rockets and so on, but it's something equivalent to that. It was sort of totally disrespectful of him. So he started the lecture by saying zeta 3 is irrational, and believe it or not, there were howls and catcalls from the audience. This was not howling in praise. I mean, in America, sometimes you want to cheer somebody, you start howling, right? Like wolves. But here, here the howling, and our Indian students have learned that. I mean, I now go to our Indian get-togethers and I find somebody is dancing and then people are howling, you know, like they do here in many of these American games and so on. Anyway, so this was howling in sort of total disrespect to Upper Reed. So then he wrote down an identity, and the audience will ask, prove. He said, I don't know, I found this in my garden. Then the next identity, and so on. And after a series of about 6, 7 identities, he says, irrationality of zeta 3 follows. And he just left amid boos and catcalls. But sitting in the audience was Henri Cohen and Don Zagier, who were very brilliant mathematicians, but not just that, they are computers, human computers. They calculate with enormous speed. And then by the time the lecture was over, they said, identity 1 is correct, identity 2 is correct, and so on. So by the end of the day, everything he had stated was correct, and he had proved the irrationality of zeta 3. And this was totally taken, everybody was taken aback by this. And when Serre, the god of France, you know, the chief of the Bourbaki and all this, heard about this, apparently he said, you know, this is not the way to do mathematics. So what? I mean, he proved what the others couldn't prove, and one has to accept it, right? So you just have to accept it. So anyway, that's what happened. So we don't know anything about zeta. We don't know the value of zeta. What value? That's undetermined. It is conjectured that zeta 3 could be the product of 3 logarithms of algebraic numbers. I mean, that is coming from the fact that you have pi squared, pi cubed, and so on. Pi is a logarithm related to a logarithm of an algebraic number, right? So that's a conjecture. We're nowhere close to it. Okay. Now what I'm going to do is I'm going to show you an interesting hacker, which I think at least 2 students in this class might pursue. And I'm going to leave it with a little bit of fuzz. I'm going to prove something, but there is a detail that needs to be worked out, and like I did for the zeta, you might be interested in pursuing. Okay. So this is an alternate way to do the analytic continuation of the Riemann zeta function. And this is related to the Bernoulli polynomials in the Euler-Maclaurin series, but I'm not going to do it that way. So I have it in my notes because when I was a graduate student, my professor Ernst Strauss just made this comment, Krishna, you can extend the Riemann zeta function step by step, 1 unit at a time to the left. He just made this statement. So when I gave this course on the Riemann zeta function, I worked out the details of this comment that he made when I was a graduate student. So I'm going to tell you what this is. So it's quite interesting. So, a step-by-step analytic continuation. It's quite interesting. Of zeta s. Okay, what is the step-by-step analytic continuation of zeta s? So, we already know the first 2 steps. Recall that we wrote the Riemann zeta function as the integral from 0 to infinity d integral part of x over x to the s. Remember, we started like this. And then, after we did that, we did integration by parts. I'm going to get to the heart of the matter, that's why I'm going.